I will try it. I scream, I will try it, Okay, good morning, everybody. I'm Gabriela Barenboim, and I'm originally from Argentina, so this means I'm half Italian already, okay? As most of our Argentinians. I'm half Italian. Okay, so let me start. I changed the title of my talk from a very boring title, Introductory Lectures to Neutrino Physics, to Neutrinos where the beyond the standard model physics begins, because I hope to convince you that one or the other, we have already discovered physics beyond the standard model. Neutrino masses, one way or the other, no matter how you see them, imply physics beyond the standard model. And this is extremely important because I have been hearing lately, as you know, 2 weeks ago was Susi in Madrid, and people are constantly saying, so this is my fair disclaimer, that 2012 was the last major discovery in particle physics, and especially this is so because this year Peter Higgs passed, and these people are referring, of course, to the 4th of July announcement of 2012 by both the CMS and Atlas collaboration of a 5 sigma 4-ish sigma evidence of a Higgs particles 125 in both in the gamma-gamma channel. And this officially started the race for physics beyond the standard model, although we have been looking for physics beyond the standard model already for quite some time. But in fact, this year didn't have one major discovery in particle physics. This year have two major discoveries in particle physics, and the one which I'm now calling the second happened before the 4th of July announcement because it happened in May. And it was the announcement by the Diabase collaboration of a 5 sigma evidence of a reactor mixing angle of a theta 1,3 different from 0, again at the 5 sigma level. And this was soon followed by the Reno experiment. And this, as exactly in the same way as the Higgs opened officially the race for physics beyond the standard model, this discovery opened its own race. We are going to talk about a lot. And this race is called by experimentalists the race for CP violation in neutrino oscillations. I will call it the search for even more physics beyond the standard model. Okay, but to understand where all this starts, we have to make a jump backwards in time, approximately 100 years. 100 years, the situation was really, really different. You know what happened here in Florence, a young adult, as we say now, which was essentially naked, living on the streets. David, I hope you have met it already. If not, you shouldn't miss it. Was able to move to a fantastic location in the still naked though, but she shares, like most of you. Now a young adult cannot move to a central location in the city center, not even sharing. The situation in physics was also very different. Okay, if summer school existed, we have just here that the school was organized here approximately 100 years ago, and I imagine if existed was very, very short, especially if it was about particle physics, because there were not that many particles around. Of course, beta decays was known and was supposed to be a two-body decay. And you know what happens if you have a two-body decay. The masses, the energies of all the particles involved can be explicitly written down in the terms of the masses of the particles involved. Let me show you. If you assume momentum conservation, this means that the momentum of the neutron is equal to the momentum of the proton plus the momentum of the electron. These are 4 momentum. This means that in the rest frame of the neutron, the moment of the neutron is the mass of the neutron, 0. The momentum of the proton is whatever energy the proton has, P, and the momentum of the electron is whatever energy the electron has, minus P. So if you go back here, Pn minus Pe is equal to the momentum of the proton. If you square it all, this is just the mass of the proton square, and this is nothing but the mass of the neutron square minus 2 times the energy of the electron, the mass of the neutron, plus the energy of the electron square minus P square. But this is again minus the mass of the electron. This means that the energy of the electron is nothing but the mass of the proton plus the mass of the electron square minus the mass of the neutron square divided 2mn. It's completely written in terms of all the masses of the particles involved. However, this spectrum was not found to be the delta you suppose by energy conservation. It was found a continuum spectrum. It was even more problematic than that. The recoil of the nucleus, this means the momentum of the emerging proton, was not opposite to the momentum of the electron. So the problem was not that energy was not conserved. Momentum was not conserved either. These people were not stupid, okay? They thought about a third particle being involved into the game, but they didn't find any evidence of either mass or charge. And this is when they started to entertain the idea that maybe energy was not conserved. But again, these were not silly people. We are talking about people like Bohr here, okay? You have to think that at that time, statistical mechanics was thriving. So the idea was not just energy is not conserved. It's maybe energy is not conserved on an event-by-event basis, but rather on a statistical basis. And this is when our first hero applies. Now psychology has evolved a lot, and we know that if your mommy dresses you up in this way, something very dramatic is going to happen in your life. She didn't know that. She is the mother of Wolfram Pauli. She dressed him in this way, and something very dramatic happens in his life. He postulated the existence of a new particle. He didn't call it the neutrino back then, but this particle has no mass or no charge and was able to restore energy conservation. But as I said, that was then and this is now. At that time, people didn't embrace the existence of new particles just because you postulated that. It's not like today, you have 5, 6 particles postulated per week on the archive. This was not the situation back then. The community didn't embrace easily this new particle postulated. It took another hero. He is also, we have heard from here, he is Enrico Fermi, and he formulated a theory of beta decay in terms of 4 component spinors using this postulated particle, the neutrino. This, together with the Fermi golden rule, allow him to calculate explicitly the spectrum of the electron emitted in beta decay, and this was found to be exactly what you were measuring this in the experiment. At this point and not before, the community embraced this existence of the new particle, the neutrino. But now that we talk about a fermion described by spinors, is the first time to understand why neutrinos are so different to the rest of the fermions in the standard model. So you know that the Dirac field is described by a 4-component spinor. Let's think about the electron, for example. In the case of the electron, 2 of these components are assigned to the left and the right-handed components of the electron, and the other 2 to the left and the right-handed components of the positron. Now imagine that I'm standing still, which is a lot to imagine, and in my frame of reference, an electron is moving in the positive z direction. The projection of its spin along its direction of motion is minus a half. I'm seeing a left-handed object. Now, one of you who are younger and fitter than me starts running in my frame of reference faster than my electron in my frame of reference. In such a way, for this person, the electron is moving backwards. He is seeing a right-handed object, and this person can ask me with which of the 2 right-handed objects in my spinor he has to identify what he is seeing. I'm going to say, this is a very silly question. Look at the electric charge. The electric charge is a Lorentz invariant quantity. If you see the electric charge, you will immediately know you are talking about the right-handed electron and not the right-handed positron. Well, what would happen if your particle does not have a charge? If your particle does not have a charge, you have several ways out. For example, you can assume that your particle has 0 mass. If it has 0 mass, if moves at the speed of light, if it's left-handed in one frame of a reference, it's left-handed in any frame of reference. You can never reverse its direction of motion. It's moving already at the speed of light. But of course, it's not up to you to decide whether your particle does or does not have a mass. What would happen if your particle does have a mass? Well, you still have several ways out. For example, you can impose a U1 charge to your particle and call it lepton number. But this new charge you are imposing by hand does not dictate the symmetry. It's dictated by it. So there is nothing sacred about this charge, but you are welcome to put it if you like it. Okay? If you impose it and if you like it, you have a four-component spinor and you have a Dirac neutrino. Fine. But maybe you don't want to impose a U1 charge by hand for no reason whatsoever. Okay, a symmetry which, on the other hand, is not protected by all. In this case, there is no way you can distinguish between the two left-handed or the two right-handed components of your spinor, and then you may get rid of half of the degrees of freedom because there is no way of telling them apart. If you do that, you will escape your particle by a two-component Weyl spinor and will be a major and a neutrino. Now with that, we move to the standard model. As you know, the standard model is based on the gauge group SU23 cross SU2 left cross U1 of hypercharge, but neutrinos interact only weakly. So we care only about the electroweak sector of the model, which is broken thanks to the Higgs mechanism to U1 electromagnetic. And you know what happens. The left-handed components of both up and down quark are assigned into doublets, while the right-handed components, again, of both up and down type quark are sitting in singlets. The situation is different in the lepton sector. Left-handed components of charged particles and left-handed components or neutrinos, charged leptons, are assigned into doublets. However, in the standard model, only the right-handed charged leptons are given singlets. There are no singlets for the right-handed neutrinos. And you know the consequences of that. A mass term is just a left-right interaction. So if you forbid the existence of a right-handed component for the neutrino, what you are doing is you are forbidden the existence of a dimension 4 mass term for the neutrino, and as a consequence of that, in the standard model, neutrinos are massless and they move at the speed of light. But the standard model teaches way more than that to us. The standard model teaches us how neutrinos are produced or absorbed. Neutrinos are produced or absorbed through neutral current and charge current interactions. In charge current interactions, they are produced in pairs, in association with the charged lepton. In neutral current interactions, they are produced by pairs. I can even calculate in the standard model just what is the width of a Z boson to any pair of fermions. So if I measure now in the lab the lifetime of the total width of the Z boson, and I start subtracting the width to all the particles I measure that leave a trace on a detector, this means the width of the Z decay into charged particles, I'm left what is called the invisible width of the Z boson, the decay of the Z bosons to particles which do not leave a trace on the detector. If I now divide this nominal width, this width I measure, by the nominal width to one pair of neutrinos, what I'm doing is counting the amount of neutrinos that couple to the Z boson. This was done long ago, and this number was found to be with an amazing precision exactly equal to 3. So if I would like to introduce, which I am eventually will at some point, to introduce more neutrinos, light means masses which are lighter than the Z over 2 into the game, I better be sure that these neutrinos do not couple to the Z boson, and this is why I'm going to call these neutrinos sterile neutrinos. Okay, this is what I mean with sterile neutrinos. Notice also that in the standard model, neutrinos are produced through charge current interaction in association with a charged lepton. This will mean that I will call my neutrinos according to the charged lepton they are produced in association with. I will have an electron neutrino, I will have a muon neutrino, and of course I will have a tau neutrino. Notice also that standard model interactions seem to preserve this U1 charge I was mentioning before. If I assign lepton number 1 to neutrinos and negatively charged lepton, and lepton number -1 to antineutrinos and positively charged lepton, standard model interaction seems to preserve this lepton number. This lepton number seems to be an accidental symmetry of the standard model. Even more than that, individual flavor lepton numbers are preserved by standard model interaction, but these ones not gonna last, so I'm not gonna even bother mention now individual flavor lepton number. Notice also that weak interactions are left-handed. And this means that through the standard model interactions, I can only produce left-handed neutrinos or right-handed antineutrinos, but I can only detect left-handed neutrinos and right-handed antineutrinos, again, through standard model interactions. And as a remark, remember that my neutrinos in the standard model are massless. This means that helicity and chirality are exactly the same thing. Helicity is a good quantum number. Okay, here because neutrinos, of course, are massless. But now that we talk about left and right, it's a good point to open a parenthesis and discuss a little bit about discrete symmetries in nature. As you know, there are three fundamental discrete symmetries in nature, which are parity, time reversal, and charge conjugation. Parity is just to flip the sign of all your space component, okay? Just to look at your process in a mirror. Time reversal is to flip the sign of the time component, to play the movie backwards. And charge conjugation is just flip the sign of all your quantum numbers, go from particle to antiparticle. Each of these symmetries is individually preserved in quantum mechanics or classical electrodynamics. This is not true in field theory. In field theory, the only thing that is preserved is the combined operation of the three in whatever order you want. This is the famous CPT theorem we are going to discuss again tomorrow, which says that any local relativistic quantum field theory which preserves Lorentz invariance, automatically has CPT built in. And the amazing thing is that under CPT, a left-handed particle turns into a right-handed antiparticle. And remember, in the standard model, we can only produce or detect left-handed neutrinos or right-handed antineutrinos. This will mean that standard model-wise, my model will be CPT complete, or would make a very healthy local relativistic quantum field theory describing neutrinos with only a two-component spinor, only a Weyl spinor containing a left-handed neutrino and a right-handed antineutrino. Okay, again, this is all fine. So in summary, for the standard model, we see that neutrinos come in three flavors. They are electron neutrino, muon neutrino, and of course, the tau neutrinos. Remember that the neutrino, it has negative helicity, okay? It's left-handed, and the antineutrino has positive helicity. It's right-handed, and helicity and chirality are the same thing. And the left-handed neutrino and the right-handed neutrino happen to be CPT conjugated states. Now, what would happen if I try to go beyond the standard model? If I try to go beyond the standard model, the first thing you can think about is to give your neutrinos a mass. But once you decide to give your neutrinos a mass, this opens a full Pandora box, because you have to decide whether mass eigenstates are exactly identical or not than interaction eigenstates. The mass eigenstates, remember, are the asymptotic states of the Hamiltonian. And you may say, why wouldn't even I consider that? Why would I care about that? Because you already saw this happening. In the case of quarks, we already know that mass eigenstates are not identical to interaction eigenstates. We have a CKM matrix. Okay, so the first thing you may ask is, this is again happening exactly the same in the neutrino case. But in the neutrino case, as we are going to see, if mass eigenstates are not identical to interaction eigenstates, you are able to have a neutrino can change flavor as you propagate. We are going to call these neutrino oscillations, and we are going to discuss why this is not happening with quarks, or maybe it is, and we haven't never noticed, okay? So we are going to work out what are neutrino oscillations in the case of two flavors, and I'm going to extend it to three flavors afterwards. So we are going to assume that we have in blue two mass eigenstates, nu mu, nu 1 and nu 2, and two flavor eigenstates, nu mu and nu tau in red, and this is a rotation in a plane. So to go from one basis to the other is a rotation in a plane, and if you know, it's parameterized by one angle, which I call theta. But if I said to you already once, and I will keep saying you many, many times, that you detect neutrinos and you produce neutrinos as flavor eigenstates, why should I care about mass eigenstates at all? Why cannot live without even talking about mass eigenstates? The problem is that, as I said, mass eigenstates are the asymptotic states of the Hamiltonian, the eigenstates of the Schrödinger equation. These are the states you know how to propagate. This is the problem. The only states you know how to propagate are the mass eigenstates. These are the states which evolve with a phase as time goes by, as Schrödinger says. This is why you care about mass eigenstate. So let's start. We produce a muon neutrino, and my muon neutrino is this combination of the first mass eigenstates and the second mass eigenstate. Now I let my muon neutrino evolve. Okay, my neutrino will start traveling, and each mass eigenstate will travel according to its phase. Remember that this is for momentum. So P dot x is, if you want, ET minus PL, okay? This is what is inside for each of them, okay? Now I want to detect my neutrino. Again, I have let my neutrino travel some distance. I want to detect it back. So this means I need to rotate back to the flavor eigenstate basis, and you do it, okay, not with this one, but the transpose of this one, okay, in this way that you have that. If you do that, if you let me do it quick, what you would have is that your evolved muon neutrino will be cosine theta e to the minus I p1x times cosine theta mu minus sine theta nu tau plus sine theta e to the minus I p2x sine theta nu mu plus cosine theta nu tau. This is what you have, and then you may decide to calculate the probability of detecting a neutrino different to the one you originally produced. The probability of calculating a nu tau, and you know how to do that. This probability is nothing but nu tau nu mu of t, if you want, square. So if I multiply this by nu tau, this means this will die, and we will get only these two terms as there. Okay, let me go with there. Now I'm going to assume that all the neutrinos are produced with the same energy in such a way that the momentum they have for each mass eigenstate are different. I can assume that they are produced with the same momentum. I'm going to get the same answer. And you may ask, which is the correct one? Neither, okay? But both of them are excellent approximation of what's going on. And if they all have the same energy, this means that the momentum is E squared minus mi square root pi, and this is E minus mi squared over 2E, okay? This is what you have in such a way that this factor you have here, there you are, has a term which is common to both terms, has a factor which comes to both terms, which is this factor here, and has a factor which is unique to each of them. But notice that I'm taking the absolute value to calculate the probability. And the term which is common is a phase, and the absolute value of a phase is 1. So you can get rid of that. You can, without any remorse, just cross this term and forget about it, because it will die natural death, okay? So it's the absolute value of a phase in such a way that whatever remains is this one. But now that I learned the trick of removing a phase proportional to the identity, I can do it again and rewrite this as e to the I m1 m2 square plus m1 square L over 4e to the minus I m2 square minus m1 square L over 4e minus e to the I m2 square minus m1 square L over 4E. And you can check that this is exactly what I have in the absolute value there. Okay? It's exactly the same, but you can just cross this term because you are removing an absolute value with a phase. This is 2, if you divide this by 2i, I again is a phase, forget about that. And this is just the sign, and this is what you get there. The only thing I'm used is that this 4 times sine square cosine square is sine square of 2 theta. This is the only thing I have done. People call this the kinematic phase, and I will call this many, many times the kinematic phase. Although I haven't said this explicitly, I have been working so far in natural units. You can see it there, okay? Because I put in EP, everything with the same units, in units where h bar is equal to c is equal to 1. If I want to restore the units to these games, I have to put the h and the c's in the appropriate places. The way to do that is completely unimportant. The important thing to notice is that h bar comes in the denominator in the kinematic phase. So whenever I'm going to be about to take the semi-classical limit, this phase will blow up. Pay attention, it's going to happen soon. So to remind you what we have done, we have produced a flavor eigenstate. Each flavor eigenstate has, we divided it into a mass eigenstate component. Each mass eigenstate was evolving according to its phase, given by form, momentum, and energy. We have recollapsed it back to the flavor eigenstate and calculated the probability of finding a neutrino different to the one I originally produced, what is called the appearance probability. I could have as well calculated the disappearance probability or the survival probability. So the probability of my muon neutrino remain being a muon neutrino. I'm working only with 2 flavors. This means that my muon neutrino can either turn into tau neutrino or can remain being a muon neutrino. It cannot do anything else. So this disappearance probability is just 1 minus the appearance probability I have calculated before. Let's look at this disappearance probability in a little bit more of detail. To make contact with the literature, the different literatures you have been using, people call this, I will call this, the oscillation length. Now let's plot this survival probability as a function of the oscillation length, or as a function of the kinematic phase if you want. As a function of the kinematic phase, you can think about this. The first thing you notice is that the possibility of seeing or not seeing oscillation is not for you to choose. It's for nature to decide. The amplitude of the oscillation is given by the mixing angle. Final point, okay? So if nature is mean, no matter how clever you are not going to see oscillations. However, if nature is generous enough to open up the window to see oscillations, okay, making this mixing angle important, then the choice of your experiment, the design of your experiment, the kinematic phase, plays a fundamental role. If this kinematic phase is miserably small, oscillations essentially do not have the time to develop. You see a survival probability of 1. If this kinematic phase is, let's say, of order 1, let's say between 1/2 and 2, between 1/3 and 3, you see a beautiful oscillation pattern. Okay? You see the oscillation in full glory. However, if this kinematic phase is huge, is very, very large, you cannot resolve the oscillations, okay? They average away. The oscillations average to 1/2, and the interference pattern is lost. We say that neutrinos propagate as effectively incoherent mass eigenstates. Okay, the oscillation is lost. Technically, this means the problem became classical. We talk about probabilities and not amplitudes any longer. And this is, by the way, what happens in the case of quarks. In the case of quarks, you are always in the incoherent regime. We are going to talk more about quarks later, but you have seen this before when you were in undergraduate school. You have seen this interference pattern appearing and disappearing before during your quantum physics courses when you were discussing the double slit of the Young experiment. Remember the Young experiment. There were 2 slits. If you were picking with which slit your particle went through, the interference pattern was not appearing. If you were not peaking, the interference pattern appeared. This is exactly what is going on here. We are going to analyze what we, go ahead. This one, because here oscillations are really too fast to be resolved. You cannot resolve them, and they average to a half. So I have been averaging them with a half. So you see a flavor transition and not flavor oscillations any longer. And this is the language you use in the case of quarks. You talk about flavor transitions, never ever about flavor oscillations. Okay? Yes, I can do that. But I'm going to talk more about coherent loss in a way. But this is, yes, essentially, you have a smearing in energy. So you have to smear over your energy resolution. This is what happens. But this is what happened in the case of the double slit or the Young experiment. Remember what happened in the double slit or the Young experiment? So we are going to describe exactly this in the double slit experiment. I produce a muon neutrino. My muon neutrino has a probability now, I'm in classical regime, has a probability of going through the first mass eigenstate, which is cosine square, and a probability of going to the second mass eigenstate, which is sine square. Now it's classically, I have peaked, so it went through the first mass eigenstate or through the second mass eigenstate. I have nothing to say about that. If it went through the first mass eigenstate, sorry, it has a probability cosine square of making a muon neutrino. If it went to the second mass eigenstate, it has a probability sine square of making a muon neutrino. This means the total combined survival probability will be the first path, cosine square, cosine square, cosine to the fourth, plus the second path, sine square, sine square, sine to the fourth. Okay, this is what is happening there. This, what I'm discussing now, is coherence loss due to wave packet separation, okay? This is something you understood. But in order to see oscillations, you not only need that, you need production and detection to be coherent as well. This means I have to be sure that I produce a coherent superposition of mass eigenstates, meaning that I shouldn't be able to kinematically distinguish which is the particle I'm producing. My energy resolution should be able to hide the difference in the masses between the different mass eigenstates. This is why in the case of quarks, if you produce a U quark, no matter how bad your resolution is, won't be enough to hide the top there, okay? In the case of neutrinos, we are lucky that the mass differences are so small that in the energy resolution, I can hide the difference because energy is conserved. Remember, now we conserve energy. Okay, so in order to see oscillations, I not only need coherence in the propagations, but also coherence in the production and in the detection. And this has to do with energy resolutions, whether I can get it or not. But in fact, life is more complicated than that. In fact, I don't have two neutrinos, but I have three of them, which means that my mixing matrix is way more complicated than that. We are going to do the calculation of the mixing matrix for n generation of neutrinos and see what happens with three later. So we have the calculation done if we want to include more neutrinos or more sterile states or whatever. So if you have n generations or n families, if you want, your mixing matrix is a unitary matrix containing n square parameters. You have n square parameters. Some of these parameters are phases. Some of these parameters are angles. You know that this is, you have n times n minus 1 over 2 angles and n times n plus over 2 phases. But as you know, not all these phases are physical. You can redefine your fields to absorb away and physical phases. However, the nature of your field is extremely important. If I have a 4-component spinor, this means if my neutrino is a Dirac neutrino, you can redefine, you have in principle 2n fields to reabsorb away all these phases. But one phase you cannot mess up with because one phase is lepton number, so it's meaningful. So you can only get rid of 2n minus 1 phases, Okay, this means that you have n squared plus n minus 4n plus 2, meaning n squared minus 3n plus 2 over 2 phases, and this is the famous result n minus 1, n minus 2 over 2 phases, which got the Nobel Prize for Kobayashi and Masukawa because they shown that in the case of quarks, you need 3 families to have a meaningful phase, okay, CP violation, this phase. And the result stands here for Dirac neutrinos. Okay, so you need 3 families to have a phase. However, if your neutrinos are Majorana particles, you have half of the degrees of freedom. So you cannot play this game any longer, but you cannot care about lepton number because it's not a meaningful symmetry in your theory. This means that in the case you have Majoranas, you have n minus 1 because you can use only n phases to reabsorb your field. So you have n minus 1 phases more if your neutrino is a Majorana particle. And these phases, the Majorana phases, are going to appear only in those processes my neutrino is forced to show its Majorana character. And these processes are not oscillations. Okay, we are going to discuss these processes tomorrow. You will hear even more about these processes today. But if you go again to 2 families, you can see that you have none of these phases. You have one Majorana phase, but plays no role into oscillation, and you have one mixing angle, and what we have seen, it's all valid. But before going on, I will say many, many times today that the physics we have here is the same physics you have seen in the case of quarks. I will claim that this regime is more favorable, but the physics is the same you have seen in the case of quarks. However, you may argue that in this case of quarks, you were taught in graduate school that flavor-changing transitions are gene suppressed. Are not they gene suppressed here? Of course they are gene suppressed here. Okay, any of the flavor transitions will go to 0 if the mass differences go to 0. So you exhibit the same gene suppression. The fact that we are able to beat the gene suppression by the careful choice of the kinematic phase does not mean the gene suppression does not exist. Of course it exists here because, as I said, the physics is identically the same. So let's start about the oscillation probability, the appearance probability, if you want, again. As I said before, all you have, the handle you have in your experiment, your ability, once nature was generous enough to put a mixing angle that gives you the opportunity to see oscillations, the kinematic phase is fundamental. So let's look at this kinematic phase in a little bit more of detail. As you know, phases are dimensionless. So in an ideal world, I would like to talk about the mass differences in electron volt squares, the baseline lengths in kilometers, and the energies in GeVs. But this is a horrible mismatch in units. So what is the price I have to pay for this mismatch in units? It's not important, okay? It's just to put there a 1.27, 5/4 essentially. So from now on, each time we discuss a neutrino experiment, we are going to talk about the mass differences in electron volt squares, the distances in kilometers, and the energies in GeVs. Even more than that, you will already know that if my kinematic phase is of order 1, I should be able to see oscillations. But if I'm not seeing oscillations, I'm seeing flavor transitions, for example, but I don't see the oscillation features, so neutrinos are propagating as effectively in coherent mass eigenstate, I will also be able to put a lower bound on the mass difference of the neutrinos involved. But if you notice about when you study an experiment, the important thing really is not the distance traveled by my neutrino or the energy of the neutrino beam. The important quantity really is L over E, and all the experiments can be analyzed by looking at the L over E. So I'm going to describe all the neutrino experiments in 3 big categories. Atmospheric neutrinos or neutrinos from accelerator, neutrinos whose L over E is around 500 kilometers over GeVs. So you already know that this experiment explored mass differences of the order of 10 to the minus 3 electron volt squares. You already know because the kinematic phase has to be 1. Then I'm going to talk about reactor neutrinos or neutrinos from the sun, neutrinos who explore an L over E of 15 kilometers over MeV, or properly saying 15,000 meters over MeV. So experiment with Explorer are sensitive to mass difference of the order of 10 to the minus 5 electron volt squares. And then at last, I'm going to discuss, probably in the second lecture, all sorts of experiments from reactor, from accelerators, from all sorts of experiments, even from the sun, whose explore L over E's of order 1, GeV, kilometer over GeV, or meter over MeV, with the experiments which are confirmed. Okay, so let's start with atmospheric neutrinos. You know that cosmic rays hit the atmospheres, they produce protons decays to pions decay to neutrino, and if your detector happens to be, for example, a water Cherenkov, you cannot distinguish neutrinos from antineutrinos. So if you count two of them with muon flavor, you have to have twice as much as those containing muon flavor as you have with electron flavors. The math is very easy. These experiments were done in the late 80s, early 90s, and this ratio was found to be close to 1, not to 2, but we were completely clueless. We didn't know where we are having an excess of electron neutrino, we're missing muon neutrinos. We didn't know what was going on, and then a miracle happened. So a young postdoc, I think, or a very senior graduate student, which we are going to have here, Kajita, realized the way to distinguish muon neutrinos from electron neutrinos. I mean, I sincerely hope he will tell the story. If not, just ask him that, because this was the birth of the neutrino physics as a serious science. Final point. Okay. Before that, this was not serious. He just jumped neutrino physics to a completely different level, because after his major breakthrough, we were able to study muon neutrinos and electron neutrinos independently. And this is what the Super K experiment does. Because the Super K experiment is based on nothing, on the Gauss theorem, okay? The divergence theorem you study in calculus. Remember the divergence theory. So you say, if you have no surface to drain inside, whatever enters the surface should be exactly equal to whatever leaves the surface, okay? Zero divergence. This is Gauss, okay? So if you assume that the flux of neutrinos is isotropic, which is a very good approximation, if you translate this to the Super K experiment, this means whatever enters the surface, whatever comes from above, should be equal to whatever leaves the surface, whatever comes from below. But this ratio, again, was not 1, was close to a half, and we were clueless, because ratios are not informative. We need to see the distortion of this number. The distortion of this number, in which direction? We need to see the distortion, how this number changes according to the distance traveled by the neutrinos. This means zenith angle. We call zenith angle, the zenith angle is the angle you obtain with the vertical. So neutrinos traveling right from your head to your detector, traveling only 20 kilometers, have zenith angle of 0, cosine of zenith angle of 1. Those traveling 2 times the radius of the Earth before hitting your detector have zenith angle pi, cosine zenith angle minus 1. So we have seen, this is what the Super K experiment produced. And you can see, for example, if you see electron neutrinos, these are electron neutrinos, nothing happens to electron neutrinos. You are just seeing exactly the amount of electron neutrinos you expect. However, half of the neutrinos coming from below and missing in the case of muon neutrinos. You can see that. And of course, we explain this with oscillations, okay? Oscillations, of course, of muon neutrinos into tau neutrinos, because nothing is happening to electron neutrinos, so they have to oscillate into taus. With this mass difference, 10 to the minus 3 electron volt square, and a mixing angle of approximately pi over 4, which we call it maximal mixing. We don't call it maximal mixing because you cannot go beyond pi over 4. You can go beyond pi over 4, and we will go in the second lecture beyond pi over 4. We call it maximal mixing because pi over 4 is the magic number in which, remember, the amplitude of the oscillations goes like the sine of 2 times the mixing angle. So for pi over 4, the appearance probability, or if you want the disappearance probability, can take all the values from 0 to 1. This is why we call this angle maximal mixing. However, up to here, I have been a little bit misleading you because I show you this plot and I claim that this means that neutrinos are oscillating. No way. No way. The only thing I'm showing here is half of the neutrinos coming from below are disappearing. But I can explain away this by assuming that neutrinos decay, for example. If neutrino has a finite lifetime, it's obvious that those traveling more distance are going to arrive in less quantities. I mean, lifetime 101, okay? So this is what you expect. The only way you should be convinced, or I convince you that we have seen neutrinos oscillations, is by seeing the trademark of oscillations. This means the kickback of the regeneration patterns. What you see, the kickback on the regeneration pattern, will you start to believe that neutrinos are oscillating. And we have seen this 20 years ago, and we are now happy with that. So we are convinced neutrinos do oscillate, and this is the favored mass difference and the mixing angles. Why I have two panels and not one, I'm going to explain in a while. And this is the place where you can get all my plots regarding best fit parameters on whatever. I will explain this more later, where I'm getting these numbers and why I'm getting these numbers from there. Okay, so, but now we have been doing this by calculating the flux of cosmic rays, if you want. Now I would like to control the experiment on the Earth, to reproduce the experiments, to be sure that I'm not missing anything, that there is not a misunderstanding about how cosmic rays behave or hadronization or whatever thing. I want to get neutrinos. These neutrinos are GeV neutrinos. They are very easy to get from an accelerator. So I can reproduce what I'm seeing with atmospheric neutrinos with accelerator neutrinos. However, I want, remember, the kinematic phase to be 1. If I want the kinematic phase to be 1, this means that if I have a mass difference 10 to the minus 3 electron volt square and energy is involved from the GeVs, the baseline should be of several hundred to 1,000 kilometers. But we have been very successful in building this baseline. In blue, you have the T2K experiment, an experiment sending neutrinos from the accelerator complex in Japan to Super K. Super K, the same Super K as detecting atmospheric neutrinos, and the same Super K I'm going to mention in a while, detecting solar neutrinos as well. This is 235 kilometers. In blue, you have, no, this is in blue. In green, you have the MINOS experiment. MINOS was sending neutrinos from Fermilab backyard, essentially to the Sudan mine in Minnesota, 730 kilometers away. And the successor of the MINOS experiment was the NOVA experiment, which it's an experiment which is also already done, was sending neutrinos from Fermilab again to the Ash River, and 110 kilometers away. So we have been pretty successful in doing that. And this is, if you look at the error bars at the numbers above and below, see how much we improve the determination of the mass difference, and especially the mixing angle, by using these accelerator neutrinos. Now I have to move and talk about the most abundant source of neutrinos we have. The most abundant source of neutrinos we have is the sun. The sun shines because there is nuclear fusion on its core. This is the energy that keeps us warm here. Although it was not warm yesterday when I was alive, anyway, but normally in Valencia, it keeps us really warm, you know? And besides doing that, the sun cooks heavy elements. The sun and any star cooks heavy elements inside. But in order to, you know the name of the game already. So if I'm going to start measuring solar neutrinos, I better be sure how many of them I expect. Otherwise, I will get no information from there. So we are going to calculate on the back of the envelope calculation, just using Wikipedia and nothing else, the amount of neutrinos we expect from the sun, and then we are going to compare what the superpros do. Okay, so as I said, the reaction that powers the sun is just 4 protons getting together with 2 electrons, making a helium-4, releasing 2 neutrinos and this amount of energy. Okay, this is the basic, all the basics you need. This means you don't have to be very smart to realize that for every 13.4 MeVs you get here in the Earth, you also get one neutrino coming along. Okay, and this MeV is this amount of joules. For this, you need Wikipedia. Okay, and then you go Wikipedia again, and you ask for the total luminosity of the sun, and a number comes, and you divide whatever number comes there from the total luminosity of the sun by 4 pi, the distance of the Earth to the sine square. Okay, you divide it by the sphere and this the distance, and what you get if you do that is the luminosity of the sun at the Earth's surface, and you have this number there. But what's remember is joule per second. So if you know that this amount of joules brings one neutrino, how many amount of neutrinos do you get with this amount of joules per second? And the amount you get is just this number per centimeter cubed per second. Okay, this is our prediction for the flux, which amounts to 2 neutrinos per cubic centimeters because they roughly travel at the speed of light. In reality, life is way more complicated than that. In reality, as I said, in the sun, you have a lot of cooking inside, and you have a lot of reactions going on, but the thing you have to pay attention is that you have two kinds of reactions. Reactions like PP neutrinos, or if you want borumate neutrinos, this one, where you have three body processes. We have seen before that if you have a three body process, the spectrum of neutrinos you expect is a continuous spectrum. Okay. However, you have like beryllium-7 neutrinos, which is a two-body process. So you know what we expect is a delta function, a monochromatic line. And then we go to what the Prost said, and this is exactly what you get. So you see the PP and the borumate are continuous spectrum, and the beryllium-7, it's a line. And if you compare what we have done with the Prost, we nail it down. For the PP, we nailed it down. We didn't even attempt to this because these are very complicated calculations. Okay, so you see, this is the amount of neutrinos you get from the sun, and this essentially says that depending on your experiment, the threshold of your experiment, the number of neutrinos you expect, and the reaction they are coming from. So if you have gallium experiments, for example, we are going to talk about gallium in a while, you are sensitive to PP neutrinos, okay, to the lowest possible energy neutrinos. Experiments like Super K or SNOW, I'm going to mention, also, they have a threshold of a few MeVs. This means they are sensitive only to borumate neutrinos. So we have been doing a lot of experiments in the years, but the characteristic of all these experiments is that the lines, the yellow lines, or if you want, the line which start yellow, are the amount of neutrinos I expect from my given experiment, okay? And the blue lines, or again, the lines which start blue, is the neutrinos I observe in the Earth. So you see that all the experiment, none of the experiment saw exactly the number of neutrinos they expected. However, they all saw different suppressions. So of course, if it worked before, it should work now. We would like to explain this with oscillations. But the first thing we need to understand is whether we are in the coherent or incoherent regime. Should I use amplitude or should I use probabilities? What is the framework when I'm working with? So we already know the answer. Look at the kinematic phase. So now we can look at the kinematic phase with enough information. So we are going to calculate the kinematic phase. This is, okay, let me go this. The mass of the neutrinos, let's say, is roughly 10 to the minus 5. This is the distance of the sun to the Earth. This is the ballpark of the neutrinos. Don't forget the 1.27, and the kinematic phase is huge. So neutrinos from the sun to the Earth propagate as effectively incoherent mass eigenstate. I shouldn't expect to see the oscillation pattern because it's not going to be there. Okay, oscillations have long been averaged away. But I need, in order to understand now solar neutrinos, I have to use probabilities and not amplitude. So let's calculate the electron neutrino survival probability. As you know, only electron neutrinos are produced in the sun, no other flavor of neutrinos. The sun produces only electron neutrinos. So we know that what is the electron neutrino survival probability is the fraction of neutrinos going to the first mass eigenstate times cosine square plus the fraction of neutrinos going to the second mass eigenstate times sine square. We have already done that. If I can describe this as two flavors, this means that F1 and F2 should add up to 1. And of course, if neutrinos were produced at the very center of the sun, as if they were produced in vacuum, I already calculated that. F1 is just cosine square, and F2 is just sine square, and this survival probability is completely energy independent. It's pretty easy. And this is the answer you have. We calculated that, and this is apparently what's going on with the lowest energy neutrinos, with pp and beryllium-7 neutrinos. In the case of pp and beryllium-7 neutrinos, the survival probability, the fraction of neutrinos which arrive to the Earth as electron flavor is 60%, meaning that they are produced as 70% in the first mass eigenstate and 30% in the second mass eigenstate. The situation is completely different for boron-8 neutrinos, and this is different because of the SNOW experiment. The SNOW stands for Sudbury Neutrino Observatory, was an experiment measured boron-8 neutrinos exactly in the same way as Super K. The difference is that Super K is a huge and massive 50 kiloton water Cherenkov detector. SNOW is a very small 1 kiloton detector of heavy water. You cannot have 50 kilotons of heavy water, okay? But the fact that this is heavy water and not pure water means that it can detect neutrinos not only through charge current interactions, but also neutral current interactions and electric scattering. But I don't care about electric scattering. I only care about neutral current interactions in such a way that SNOW is a standalone experiment. If you assume that there are no sterile neutrinos involved into this game, through neutral current interactions, you measure all the neutrinos that come to the sun, regardless of their flavor. With charge current interactions, you measure only those who have electron flavor. So if you calculate the ratio of neutral current to charge current or neutral current interactions, what you are doing is calculating the survival probability. You can also use your neutral current, what you have observed as neutral current interactions, to check the involvement or to bound the involvement of sterile neutrinos in the sun. You can also use that to compare what you are observing, what you should observe, if the sun produces only active neutrinos and put a bound on sterile neutrinos. The SNOW experiment has done it all, but if you do this game, if you use the survival probability as the ratio of what you have observed as neutral current, charge current over neutral current interactions, and you assume F1 plus F2 is equal to 1, this means that the two flavor description is a reasonable description, you can calculate by this the fraction of neutrinos produced in the first mass eigenstate, and you find that this miserably small is 10%, meaning that for boron-8 neutrinos, the survival probability is 30%. They are produced 90% in the second mass eigenstate and only 10% in the first mass eigenstate. The survival probability is half what we have seen before. We have seen before that for pp and beryllium-7 neutrinos, the survival probability was close to 60%, meaning that they were produced 70% in the first mass eigenstate, 30% in the second. We are seeing now that boron-8 neutrinos have a survival probability which is much lower than that, and they are essentially a mass eigenstate, a nu2. So how can this going on? I mean, neutrinos are neutral particles. They cannot, this is not real life. You cannot depend on who your parents are. Your connections matter only in real life, not in neutrino life, okay? So for a neutrino, the survival probability cannot depend on the reaction they are coming from. So what's going on here? The only possibility that's going on here, this may be, and just maybe, assuming neutrinos are produced in the very center of the sun, as they were produced in vacuum, it's a little bit of an oversimplification. And maybe if neutrinos are produced in a very dense medium, the masses and the mixing angles change. Meaning, what do I mean with that? The coherent superposition of mass eigenstates I produce in a medium is not the same as the coherent superposition I produce in vacuum. And this is what we are going to see after the break. But for you, this is a super famous, super beautiful picture of the sun. If you see it as a picture of the sun, it's a very sloppy picture. Okay, you can with your phone can take better one. But this picture was taken 10 kilometers under the surface. Okay, so this makes a picture more serious. Not only that, it was taken not with a camera, but with 50 kiloton water camera, which is using neutrinos and not photons. Not only that, using boron-8 neutrinos, which are mass eigenstates, which by definition are non-interacting states. So this makes this picture amazing, beautiful, I mean, really, really beautiful. And I will continue after the break. Okay, thank you.